talk about Newton's second law. What was Newton's second law? Anybody remember? F equals ma. So Newton's second law, very simple to remember. Force equals mass times acceleration. Sorry, child calling me. Force equals mass times acceleration. Remember, the force is a vector. Acceleration is also a vector. Mass, not a vector. Mass just dictates your inertia. This looks really simple. Sorry, he's homesick and he wants me to approve his YouTube time and Roblox. So I'll help him during the break. Newton's second law is force equals mass times oh my God, Tyler. Okay. He does this thing where if I don't answer the phone, he just keeps calling me like a psycho. So I'm going to put this on do not disturb. Okay. Newton's second law. So here's our forces, right? If we add a mass, here we have a large mass. Here we have a small mass. This is an empty cardboard box. This is a large safe. Obviously, children are always pushing large safes around. What's going on with the acceleration? Which one's going to have more acceleration? The box, because these are the same force, but this is a larger mass. The smaller mass is going to have more acceleration. And I spent a lot of time animating that, so I'm sorry. You have to watch it now. So that's the large acceleration. The other thing is, remember, we have to talk about the net force. So the acceleration always points in the direction of the net force. Going back to this slide, if our net force points in this direction, then the acceleration also points in the same direction as the net force, okay? So not each force vector has its own acceleration. You have to look at the whole system. The acceleration points in the direction of the net force. So if you really wanted to write the F equals ma nicely, it looks something more like this. So sum of all the forces, right? So you sum up all your force vectors, and it's equal to mass times acceleration. So all of your forces added up give you your acceleration, and it's proportional with the mass as the proportionality constant. Okay? Quick clicker question. So if you have all of these forces, which way does this accelerate? So B, C, or D? Okay, please discuss. We'll vote again. Yes, D. So remember, when we add up the vectors, first, since these are pointing in the same direction, you would subtract them, so you'd end up with a little bit of a vector pointing down. You add those two together, it should point sort of in this direction, okay? So that means the net force points this way, which means the acceleration also points that way, and that would be answer D, okay? Keep going. I was going to save this for the break, but yeah, apparently I didn't. Okay, so what makes a Newton? This is our unit of force. Well, when we think about F equals ma, we know force has units of newtons, mass has units of kilograms, and acceleration has units of meters per second squared. Therefore, when we put this all together, a Newton breaks down into kilograms meters per second squared, which could be written as kilograms meters over second squared also. A Newton is what we call a secondary unit, meaning we've defined it by primary units, where our primary units are kilograms, meters, and seconds. Okay? The next very important thing about this is drawing free body diagrams. So these are our force diagrams. It's the dot with the arrows, okay? The way that we do this is we basically, every time we have a problem, we identify all the forces. We represent the object as a dot. We pick a coordinate system. And then we draw each force as a vector pointing in the correct direction. And if possible, we identify the direction of the net force. Like if we know where this thing is accelerating, we can sort of figure out before we even start adding things up which way things should point. Okay? When we talk about net force, remember we're just adding up all the forces. So if you have a force from the kid, you have a force from this guy, you can draw these. However, remember you can move vectors around. You also have the force due to gravity and the normal force, assuming this is sitting on the ground. This is, you want to label these, right? Because if you give them all the different, if you call them all F, it's going to be hard to keep track of things. So just for notation, normal force is written as capital N or lowercase n. It doesn't matter. Do it how you want. Or you could call it force with the subscript n. all of those are fine, but usually some sort of n is involved for normal force. It gets more complicated when we start talking about force pairs. Then we start calling it like normal force of A on B and B on A, things like that. You can label things however you want, but you probably want to pick something that's simple. And then gravity is often written as W for weight, okay, because that's going to be mass times G. We'll talk about that in a minute. So if this was your problem, you would label these things out. You would pick a coordinate system. In this case, we're picking the standard XY coordinate system that we're used to. And then if you wanted to draw a free body diagram, we now represent this whole picture as a dot, and we move these forces over to the coordinate system with the dot at the center, okay? So if we're summing up the forces in the x direction, this is Newton's second law right here. Force, sum of the forces equals mass times acceleration parallel to the net force. So we added up all the forces in the x direction, okay? Then we can add up all the forces in the y direction. Oh, and sorry, because, oh no, I've done a bad thing. So when we added up all the forces in the x direction, what did we notice? Did they equal 0? No. So that means there's an acceleration, which means there's motion. Okay. That means our acceleration is in the x direction. If we add up the forces in the y direction, what do we expect to happen? Do we think there's going to be acceleration in the y direction? No, it's just sitting there. So we add up all the forces in the y direction. That's still force equals mass times acceleration. So we add up, you'll notice the normal force, we have up and down. So up, positive, down, negative, right? Acceleration in this case is going to be 0. So there's no motion in the y direction. Okay? So when we talk about force equals mass times acceleration, it's a very simple equation, but it requires you to do all of these things. Because the force and acceleration are vectors, that means you have to sum up all the vectors, which means you have to break them into the coordinate system. So you have to decompose your vectors into x and y if you've chosen x and y as your coordinate system. So everything has to line up, because remember, you can't add things unless they're parallel if they're vectors. Okay? So you figure out all your forces, you do your vector decomposition onto your coordinate system, and then you sum up in all the directions, and then you have an answer. So it's a very simple equation that requires a lot of work. Okay? Here's an example of when you might have components. Okay? So here we have tension, but it's not along the x direction. So in this case, the force here, which you would also call tension, which would be capital T, goes in this direction. It's at an angle from the x direction. So you can break it into, components, x and y components, by using the angle. We did this triangle thing. So the x direction would be f cosine theta. The y direction is f sine theta. Okay? Then you just have the other forces. We have weight and normal force. And if we had friction, it would go the other way. But let's say we don't have friction. So now we can sum up all our forces in the x direction. We still have acceleration in the x direction. We know that because it showed that there was motion. So there's only one force in the x direction. It's in the positive x direction. It's f cosine theta. And that's equal to mass times acceleration in the x direction. In the y direction, things are a little bit more complicated because you have two forces pointing up. So you just add them up. Normal force plus f sine theta is minus weight is equal to mass times acceleration. Once again, since it's not moving in the y direction, the acceleration is 0. Okay? Now before we had n minus w and it was 0. So what's changed here? If we're assuming this safe has the same weight. So the weight hasn't changed, but we added another force up, but it's still not moving. So what's happened to our normal force?
It became lower.
It's smaller because there's a little bit of lift coming from the rope. Okay, so the normal force doesn't have to stay the same in this case. It just has to cancel out the weight and the other forces. I'm going to do an example as we do. I will just do this one as to show you how it works, and then we'll probably do a problem right after this. So the question says we're pushing a box in a straight line across the floor with a constant force, and we're pushing it at a constant speed. Okay, And so we want to identify all the forces acting on the box. So to start out with, we're going to draw the picture. So here's our picture. And in physics and engineering, we tend to draw a surface to know, if you have a line, we put these little hash marks here to show you which, I don't know why we do this, but we do it, and it's in the book and everywhere. So we're going to draw it that way. So let's say we have a box here. And we know that it's moving at a constant speed. Now, why is it useful to know that it's moving at a constant speed?
There's no acceleration.
Yeah, no, it means there's no acceleration, which means that the forces all have to cancel, right? What is our net force here? Zero, yeah. So we know the force net, when we add everything up, that needs to equal 0. And we get that from, pushing at a constant speed. That's where we're figuring that out. That tells us both this and this. Okay, so that's sort of an assumption. We also know we're pushing with a constant force. Push with a constant force, okay? So we'll start by drawing our pushing force. So we'll call this F push. Okay, you could also draw this over here because vectors are neat like that. It could go here. It could go here. It doesn't actually matter because all we care about is the magnitude and direction of the arrow, okay? What other forces would we expect to see on this box? There's going to be a force down. What's that one called?
Gravitational.
Yes, the gravitational force. We could also call that weight. And we'll talk about this later, but it's equal to mg if you want to do math on it. That's neat. What other forces do we experience? Does this box experience? Normal force, right, because it's in contact with the floor right here. So there's a force that points up. That's the normal force. Okay, these are not drawn to scale because we know they have to cancel. So those arrows should be the same, but they're not. The normal force actually acts here, but it doesn't really matter where we draw it, like we said. So it will matter later. So I'm pointing those things out because when we do things like torque and we don't treat the object as a dot, then where you draw the force starts to matter. So it's something to think about, but for these problems, not going to matter. We're going to draw this box as a dot shortly. What other force do we need to have, though? Because we see there's a force here, but we know there's no acceleration, so we know it has to cancel with something. Friction. So friction is sort of an implied force here. And what friction is it going to be? Kinetic, because we have a constant speed, which we were told in the problem. Okay, so we have all our forces. We drew them on the picture, but we also want to know what's our coordinate system going to be?
XY.
Yeah, we'll just pick XY. That one's pretty standard, and it works really well here. Conveniently, all of these forces align along XY. So if we draw out our coordinate system in order to draw the free body diagram, right? So we'll say this is X and this is Y. Over here, this is X and this is Y. We're going to draw our box now as a dot, okay? And then we're just going to take these forces and we're going to draw them on the free, I'm not going to do that. Let's see. I'm just going to redraw them. We're going to draw them on the free body diagram. So we'll take the normal force, and I'm not preserving the size of these things, but you get the idea. And then we have the weight going down, and we have our force from the push, and we have our force from kinetic friction. And we know if we use our Newton's law, which is force net is equal to mass times acceleration as vectors, we can sum up the forces in the x direction. That's going to be force of push minus friction, kinetic, which should be equal to mass times acceleration in the x direction, which is 0 in this case. But you could write this as ma and then know that it's 0. And then if you sum up the forces in the y direction, that's going to be normal force minus weight, which is equal to mass times acceleration in the y direction, but that's also equal to 0. So this is just a stronger statement of this thing that we knew from reading the problem, but all the problem's really asking you to do is draw this. Okay, I'm just giving you extra information that'll help you later. Any questions on this? Cool. So we're going to go to a problem that I'd like you guys to try. So here we have a free body diagram. We have a box that's sliding down an incline, so it's moving. But we know it eventually comes to rest due to friction. So that means that does imply an acceleration. Which way would that acceleration point? So which way is the box moving? Down. Which way is the acceleration pointing? Up, because we know it's slowing down. So the acceleration has to be opposite of the direction of motion, which means that the friction is probably the only force pointing up the slope. So take a second, draw the free body diagram for this, and then we'll work on it together. Whenever we start a problem like this, we draw the picture. In this case, they've kindly drawn the picture for us, so we can just draw on the picture. So we want to start by identifying all the forces. That's sort of our next step after drawing the picture. And we've also read the problem. That's also a very important part of doing problems, is actually reading the problem. And by reading, I mean like looking at the words and understanding what they say, because as we've noticed, there's a lot of subtext in these things. So like this doesn't say necessarily that acceleration points a particular direction, but you can assume based on the clues given that it does. So we'll start by drawing the forces. What forces are acting on this box?
Force of friction.
There's a force of friction. Which way does the force of friction point? Up the ramp, right? So the force of friction is going to be this way. Is it kinetic or static friction? Kinetic, because we know it's sliding. What other forces do we have? Gravity, right? So we have weight. Oops, this box is a terrible color. Okay, so we have weight pointing down. It's also equal to mg. Anything else?
Velocity.
We do have velocity. That's not a force. So let's finish the forces first, and then we'll talk about the velocity, right? Normal force. Which way does the normal force point? Points perpendicular to what?
The surface.
The surface of the ramp. So it's going to point this way, right? That's our normal force. It's also important to think about velocity. So we know velocity is going to point down parallel to the ramp. We'll say this is our initial velocity. What about acceleration? We can assume acceleration's direction, right? Which way does that point? Up the ramp. So parallel to the ramp, but up. And you'll notice I'm drawing the acceleration and velocity, but I don't draw them on the box. I draw them sort of over to the side just to keep track of them, but so we don't confuse them with forces, because acceleration is not a force, but it's related. So it's important information, but we don't include it. Then if we want to draw the free body diagram, we got to pick a coordinate system. Now this is where things get tricky. Remember at the beginning of class I told you that coordinate systems are arbitrary, meaning like you can pick which way they point as long as all the axes are perpendicular, okay? So you can draw the regular XY coordinate system like this in this case, but that's not a great choice. And the reason for that is this. The acceleration, if you draw a coordinate system that looks like this, that means your acceleration is not parallel to X or Y, and now you have to break it into components, which is annoying mathematically. You can, and the problem will still work. It will just be more algebra. And our goal is to be lazy and do as little algebra as possible, okay? So because we know there's an acceleration in this direction, what we want to do is choose our coordinate systems to be parallel to the acceleration. And this is generally a good strategy when doing force problems, which is to choose your coordinate system based on your acceleration, assuming you know it. So we're going to do something called a tilted coordinate system, where our x-axis is going to be parallel to the ramp, and then because, that's the rule, the y-axis is going to be perpendicular to that, okay? And in order to do that, we have to actually draw our free body diagram in the same way. So I'm going to draw it over here just because it's easier, and then I'll move it over, okay? So we have this free body diagram that's parallel to the ramp and then perpendicular to the ramp. So I'll draw out Y and X. Okay, we're going to represent the box as a dot again. And then we're going to bring over our forces. So, oops, oh geez, what the heck? Oh, I almost did it. It's pretty close to being parallel. Pretend that's parallel. I'll just redraw it. This is why it's hard to draw. Okay, normal force. We have our kinetic frictional force, but then we have this one that's not in any way parallel to an axis. So what do we do with this guy?
Split it.
Yeah, this one we have to break into x and y components. So we're going to do that, and that's going to be a little bit tricky. That's not part of this problem, but it's good practice because it's going to come up again. Okay. Now, you're saying, well, we're still breaking something up into x and y components, but we're breaking less things up, because if we had drawn the other coordinate system, that means we would have had to do this how many times?
4 times.
I think just three, right? If we pick the regular one, this one would be parallel to regular y, but we'd have to break this one, and also acceleration into x and y components to use a standard xy coordinate system. And that is very annoying because that's 3 triangles that you have to do. So when we draw this, the tricky thing here is, like, first let's pick an angle. So let's say the angle is, we'll call this angle theta, okay? But where is this angle over here? So let's draw just some lines for guidance, right? So if we think about what we know about triangles, where does theta show up over here? Is it this one or this one? So just for reference, let's draw this all the way down. So now we have this triangle, right? And now we're also going to have sort of like this triangle. Because we want to, what we really are trying to do is break this into components that look like this, okay? Although, just for cleanliness, we'll draw this vector up here, okay? So we need to figure out which is sine and cosine, but that means we need to figure out which thing is theta. So is it this angle or is it this angle? It's going to be orange, and that's going all the way back to geometry, right? So this is theta, okay? And the reason for that is this is a 90-degree angle, right? So this is theta, this is 90 minus theta. All right, if you go over here, this angle should be pretty much the same as this angle, right? These are similar angles. So this is 90 minus theta, meaning this is theta, or you can look at it like this is your 90 degrees and theta, 90 minus theta, because opposite interior. There's lots of different geometry you can do to get to this conclusion, but you might need to do a little refresher, although generally, if once you figure this one out, all ramp problems look pretty much the same, so just remember, okay? So either review your geometry or go back to this. So I'm going to clean up some of this. And we have something that looks like this. So let me get rid of all these triangles. Yikes. Okay. So we end up with theta here, theta there. So that means if we're drawing this, this is theta over here. Oops. Let me draw it in a color you can see. So this is theta. And that means if we want to break our things into components, they look like this. And remember, you're basically just making this I didn't draw it great, but this is the rectangle that we're dealing with here. Let me make that better. Okay, so really what we're looking for is this one is weight cosine theta. Why is it cosine? Yeah, it's the adjacent side to this angle, right? And then that means this is weight sine theta. And now we have only vectors on the axes that we chose that are perpendicular. If we want to do Newton's second law, we can sum in the x and y direction. So the sum of vectors in the x direction, sum of forces in the x direction, is going to be w sine theta minus kinetic friction, which is equal to mass times acceleration in the x direction, which is just this acceleration. Okay, if we sum up our forces in the y direction, that's going to be normal force in the positive y direction minus weight cosine theta which is equal to 0 because we don't have any motion in this direction. Okay? Yes?
Does net force in the y direction also equal ma?
Does net force in the y direction also equal mass times acceleration? Yes. But in the y direction, what's the acceleration? 0. So if you want to be real specific, you can also write this as MAY, but then we already know from the problem that y equals 0, and so then we just we multiply mass times 0 and we get 0. Yeah. So that's how we draw the free body diagram. That's how we pick our coordinate system. We tilt our axes, and then we can sum up our forces. This is just Newton's second law again, right? Okay. Any other questions? And this is like a new concept. Cool. Okay. So let's see. I'm just gonna not go back to the slides just so we don't have to switch back and forth. So let's talk a little bit more about the normal force. Remember, the normal force is this force exerted on a surface to prevent an object from falling through the surface. So it's always perpendicular to the surface. And we also want to just mention that the normal force is pretty variable, meaning it can change its size based on the need, because really we're defining it as, well, it's whatever force supplied by the material to make things not move. So the normal force generally is changing depending on other factors. So what that means is a surface will supply whatever normal force is necessary to prevent an object from falling through. And this is sort of in opposition to the weight, because the weight is going to be the mass, which is a non-changeable thing, times the g, which is a constant, right? So mass times g, weight always stays the same. Normal force is adjusted, right? So even if I just press on this table, right now, the normal force is smaller than if I lean forward, right? So now I'm changing the normal force. I haven't necessarily changed anything else, but applying more pressure to the table by shifting my weight around changes the normal force. We would still just draw it as n pointing up, but the normal force has shifted, okay? So normal force is a little bit trickier than weight, which is easy to quantify. Yes, it seems like you have a question.
Is that the same with like displacement and buoyancy? Because you're also pressing on it, right?
Buoyancy is a little bit different. Buoyancy, and we'll talk about this, I think, later in the class, is
because you just displace your weight, right?
Buoyancy is tricky, so it depends on if you're floating or submerged. But also, the whole point of the buoyant force is it's a pressure differential between the top and the bottom of an object, okay? And part of that is because in all fluids, because of gravity, if you go lower, like if you go deeper, even in air, there's more density of the fluid because all the fluid on top of it is pressing down. So there's this gradient of pressures as you go down. So that's why going down to the bottom of a pool makes your ears hurt, because there's more pressure pressing in on you when you go deeper. So it's a lot more pronounced in water than it is in air. But if you go to the top of Everest, a lot less air pressure, a lot less oxygen, you'll notice, right? So you're technically buoyant in air too. It's just not as useful because the weight of you and the mass of you is like much bigger than the differential in the fluid, meaning air. Underwater, the differential of the fluid as an individual object, even a small object, makes much bigger difference because the fluid's much more dense. Okay, but yeah, we have a whole chapter on that. So if you're interested in that, we'll get to it. Okay, so that's my side note on normal force. The other thing is the normal force can be considered what a scale would read. And this is important because if you're just standing on a scale, it's also, our scales are confusing in the US because they give you your weight in pounds, which is actually equivalent to newtons, not kilograms. And we convert back and forth to kilograms, which is fine because we live at sea level and that conversion can be done. But a scale is going to read something different if it's on an incline. So if you want to like lose weight real fast, just put your scale on a ramp and it's going to measure your normal force, which is not going to be equal to your weight because the vectors won't be parallel anymore, okay? Also, if you weigh yourself in an elevator while it's accelerating up or down, it will change your weight that the scale reads, meaning it's just changing your normal force. The reason a scale works really well and measures mg is if you just put on a flat surface and stand on it, then the normal force and the weight should be equal. But if you change any of those conditions, your scale's going to read something different. And this is an experiment you can do at home. You can put your scale on a ramp and you can tell people that you've lost weight. But really, you've just changed your normal force. Your weight hasn't changed at all. Okay? All right. So, normal force is what a scale would read. So here is a problem we're going to do together. How are we doing on time? We're doing good. So take a couple seconds, look this over, and then we will go over this together. So let's say this problem said that someone was pushing on the box from the left and it wasn't moving, then static friction would be an issue. Yeah.
Oh, okay.
Or like if usually there's some other force that it has to counteract, so it's more obvious. Like there's a force pushing this way, but it's not moving that way, so there must be friction. Yeah. Okay. So we're going to start by just figuring out what forces. This is a deceptively easy problem, but really we're just doing number stuff to what we've already been doing. So the forces, what are the forces? Normal force? Gravity. Okay, which we could call weight also. All right. So if we want to pick our coordinate system, which one do we pick? Just the boring one, right? So X and Y. So we draw our free body diagram. Oh no. Why is it doing that? Okay. And then, so X, Y, this is our box. We bring our forces over here, so we have normal force, and we have weight. That's our free body diagram. What do we know about the net force?
0.
Yeah, F net is equal to 0, meaning if we sum all the forces in the y direction, we know it's not moving. So if you wanted to write that out how we've been writing it out, we sum all the forces. Remember, this thing is a summation, okay, in the y direction, which is normal force minus weight, which is equal to 0 in this case, all right? It also wants to know what the normal force is acting on the box. So if we want to solve for that, we know that normal force in this case is equal to weight. We know that weight is equal to mg. We know that the mass is 3 kilograms, and let me move this over. And g is 9.8 meters per second squared. So that's going to give us 29.4 newtons. Remember, a newton is a kilogram meter per second squared. And which direction is that going to point? Which direction is the normal force? Positive y hat, right? So pointing up, essentially. You could also write up, and that's our normal force. So that answers that question. Okay? Any thoughts on this? Cool. Let's go back to our other. What happens if you push down on the top of the box? What happens to the normal force then?
It increases.
Yes, it increases. Why?
Because more mass is
Yeah, so if you push down on the top of the box, so pushing down on the top of the box means you have another force pointing down, okay? Which means this force plus this force still has to equal this force. We know this one doesn't change, so if we add a force going down, that means our normal force is the only thing that can change because it comes from the structure of the objects itself, like the material structure. So as you apply more force, that means that the normal force has to get bigger, okay? What else did I have? Oh, I had one more question. Yes?
So say you add 5 more newtons of pressure on the top of the box, would the normal force go up by 5 newtons?
Yep. Yeah. So if you add it, because remember the weight can't change. So if the weight is 29.4 newtons and you add 5 newtons down, that means the normal force has to be 34.4 newtons. Yeah. Okay. So more about the force of tension. Let's say, remember, the tension in the rope or in a rope or string is the same everywhere in the rope or string. That's the way we're defining it for now. So let's say a rope is hanging, supporting a hanging dumbbell that's 10 kilograms. What is the tension in the rope? Okay. So in order to do this, we draw a free body diagram. So that means we know there's a force of tension up. What's the force down? Gravity, weight, right? So that means because this isn't moving, the tension up has to be equal to the weight down, since we know there's no acceleration. And that means if we have a 10 kilogram dumbbell, what's the weight? 98 newtons, right? Because 10 times 9.8 is 98 newtons, which means the tension in the rope also 98 newtons, okay? And that's because the net force is 0. So just to review, when we solve these problems, we draw a free body diagram, we identify and label the forces, we write the net force equations by adding all the forces together. Somewhere in there we might want to think about acceleration, and then we use Newton's second law to solve, okay? So we're going to try an example problem. I'll do this with you. So we have a horse, it's pulling a sled horizontally with a force of 20 newtons, and the sled experiences 10 newtons of friction with the snow and 5 newtons of drag from the air, and we want to know what the acceleration of the sled is. So I'm going to attempt to draw a horse and a sled, which is neat. So here, we're drawing a picture. Here's a terrible picture of a horse. We'll make it brown. That'll help. Here's a horse. Probably has ears, right? Maybe a tail. Okay. And it's pulling a sled. I'm going to make the sled a box. It's good art. Okay. So there's the horse pulling a sled. We're given, so we know this is a 20 kilogram sled. So we're going to write that as, I'll just call that mass of the sled is equal to 20 kilograms. And we see the sled experiences forces. So let's draw the forces on the sled. The sled is our main object. So what forces do we have for this sled? Force, yes. The horse force, which I'm going to call tension. Horse force, though. I like it. Anything else? Yeah, weight, right? We'll call that mg. Anything else? Friction. Kinetic friction pointing this way. Anything else? Normal force pointing up. Last one. Drag. So we'll call that D. So drag we know is 5 newtons. We know that the kinetic frictional force is 10 newtons, and we know that the tension from the horse force is 20 newtons, and we know this is 10 kilograms. So what coordinate system do we want to use? Just the regular x, y. So we'll say x and y. So if we want to draw our free body diagram, and you don't actually, this is good practice when you start doing these problems, but once you get the hang of it, if you want to go directly from the drawing, I don't have a problem with that. But right now we're representing this. This is our sled. This is x. This is y. And we draw our forces. So we get tension, normal force, mg, and then we have to sort of represent both of these forces as friction and drag, okay? So that's that. Then, since we have to actually solve the problem, what do we want to do next? Can you see it? Some squinting happening there. Well, we use Newton's second law, right? Newton's second law says force equals mass times acceleration, but those are vectors, and we have to sum them. So we start by adding all the forces in the y direction. That one's kind of boring. Forces in the y direction, if we add them all up, that's going to be normal force minus mg, which should be equal to 0, which is mass times acceleration in the y direction. In the x direction, okay, we have tension minus friction, kinetic minus drag is equal to mass times acceleration in the x direction, okay? do we think yeah, we're solving for acceleration, so we're assuming there's acceleration. And which way do we think the acceleration probably is, going back to our drawing? Probably forward, right? Probably in the horse pulling direction, so that's our acceleration. So that's what we're solving for. So we probably don't need to worry too much about the y direction. In the future, when we're not given friction, the y direction ends up being important for solving for friction because friction is related to normal force. In this case, we're going to ignore it because they gave us all the numbers, okay? So what we want to do is solve for acceleration, and we find, whoa, that's weird. Why did it do that? Okay. We find that acceleration is going to be equal to tension minus friction minus drag over mass. Okay, so that's our equation. We plug in our numbers. That's going to be 20 newtons minus 10 newtons minus 5 newtons all over whatever the mass is, 20 kilograms. Okay, so that's going to be 5 divided by 20, which is a quarter. So 1/4 is 0.25 meters per second squared, and that's our acceleration in the x direction. It's going to be in the positive x direction, and that's our answer. And for some reason that disappeared. That's cool. Pen issues. Okay, so that's our acceleration, so we'll make it orange. Okay, yes?
Would it be 0.3? Because it's
Yeah, if you want to get nitpicky, it's 0.3. But I'm going to call it 0.25 because I was going to write it as a quarter. But yeah, you're technically correct. Yes?
So kind of piggybacking off of that, so can you write stuff as fractions?
Yeah.
Doing it as a sig fig?
That's totally fine. Sig figs, remember, I only care if you really screw them up, like you only need one sig fig and you write like 47, that would be a problem for me. If you write 0.25 or 0.3, since we're not NASA and we don't care as much about getting this right, like this class is more about practicing the concepts, so I'm not going to be nitpicky about that. I'm just going to, if you really blow it, then we'll care. Okay, so I think the specific policy on exams is if you're off by more than 2 sig figs, then we have a problem. Yeah. Okay. Any other questions about this? Cool. I'd like you guys to try this problem with the horse force, and we'll have to do it pretty quickly. I'll give you a couple minutes and then we'll go over it. What's changed in this problem? Like, do we change the drawing? No. Do we change the force diagram? No. So we could go back and just copy this and bring it over. Mainly the thing that's changed is the numbers. So since we drew it all out and solved it symbolically, we could even, keep these same equations. So that's why it's important to solve things without numbers in case it asks you to tweak the numbers on the next step. But because it's giving us acceleration, now it's asking for the force of friction between the sled and the snow. So instead of solving for acceleration, now we're going to solve for friction. So we're going to say that friction kinetic is going to be equal to T minus D. So tension, horse force, tension minus drag, minus mass times acceleration in the x direction, and then we just plug these in. So we know the horse force is still 20 newtons. The drag now is 2 newtons. And then the mass is 30 kilograms instead of 20, and the acceleration is 0.1 meters per second squared. We plug all this stuff in, and we get a frictional force of 15 newtons. So essentially, this is the same problem, just with the numbers tweaked and it's asking for a different value than we did before, but all that's just algebra. Okay. We've been talking about forces. We're talking about Newton's laws. How many of them are there? 3. We talked about the first one. Anyone remember the first one? Oh, everybody in unison. I like it. An object in motion stays in motion. An object at rest stays at rest unless a force acts on that object, okay? So that's where we're starting out with the first law. And essentially what that means, and I'm going to repeat this over and over because it's an important concept, is that something either isn't moving, although if you think about our reference frames video, everything's kind of moving. It's just like relative motion, but let's not get philosophically distracted. If something is stationary in your frame of reference, it doesn't move unless a force acts on it. If something is moving, it moves in a straight line, right, at a constant speed forever or until a force acts on it. So that's what the first law says. The second law is force equals mass times acceleration, which sounds really simple. It's an equation with 3 variables in it, except that force and acceleration are vectors. When we say force, we mean the net force on the object, so the acceleration behaves in the way that the net force is pointing. And so what we've seen is, in practice, what that means is you have to know all the forces, you have to break them down into components, meaning like x and y, or r and theta, or x and y and z, and then add them all up, and then figure out what the result is, and then figure out the acceleration. Right? So that means you have to understand coordinate systems, you have to understand vectors, and you have to set up this whole problem and draw a big picture just to do F equals ma. Okay, so that's Newton's second law. And just thinking back to kinematics, remember, dynamics is why things move, kinematics is how they move, and what's the special situation here for these equations? When can you use them? I guess more importantly, when can you not use them? Yeah, acceleration for these equations has to be constant, okay? If acceleration is not constant, these equations are no longer valid, and you go back to the definitions for motion, which are derivatives and integrals, essentially, right? So we know velocity is the time derivative of position or displacement, and that acceleration is the time derivative of velocity. And if you take a time derivative of acceleration, what do you get? You don't need to know this, it's just fun. Jerk. You could be a jerk. And then if you take the time derivative of that, you get snap. And then after that is crackle. And then pop. Yeah, so fun with cereal. Okay, but when we go back and forth between these two things, right, they're related. This is why, this is how. What's the common thing here? What variable is in both sides? Acceleration, right? So we use dynamics to find acceleration, and then we can plug it in to figure out, predict motion, right? Or if we have some situation where we know what the motion is, we can go backwards, find the acceleration, and go to force. So connecting what we learned in the first 3 chapters with what we're learning now, this is chapter 4, right? Mm-hmm. Yes? Cool. That's the big connection there, okay? All right. We have our first question. Let's try it out. Okay, we're thinking A, B, or strong contingent of D. Please discuss. We'll vote again. Okay, so this is like the worst result I've ever had this. So, definition of equilibrium. Anybody remember? That's part of the word, yes. Good start. What has to be 0 to be in equilibrium? Not everything, right? Because dynamic equilibrium means speed isn't 0. Acceleration needs to be 0 for equilibrium. So if you're throwing something up in the air, what's the acceleration? Negative 9.8. So is acceleration 0 ever here? No, right? Speed is 0, but remember that's the instantaneous speed at the peak. But the whole time, there's a net force on this object, right? And the net force is gravity, which means there's an acceleration, which is the acceleration due to gravity. So this thing is not in equilibrium at any point in this arc, okay? Because remember, equilibrium means acceleration and therefore net force are 0. So you either have to be at no speed or a constant speed, okay? And yes, speed is 0 here, but it changes immediately before and after, so that's the problem. Change in speed needs to be 0, okay? All right, cool. Just remember what equilibrium means. That really helps with this problem. All right, so let's talk a little bit about friction. So remember, we talked about these 4 fundamental forces. We have gravity, which we've spent a lot of time on. We also have the electromagnetic forces, and then we have the strong and weak nuclear forces. Well, it turns out friction is actually kind of an electromagnetic force because what's really happening is it's interactions at the molecular level. Now, you don't need to know that necessarily to use friction in a force problem, but that's what's going on. So it's more of a chemistry issue. So what's happening is basically as you rub your hands together or rub your hands on a surface, there's the most of it's like, what are those called? Hydrogen bonds? These little weak and like van der Waals interactions between different materials, but it really depends on like what the material of one thing is versus what the material of another thing is. And it's interesting because even though there's so many different materials and so many different structures, on a macroscopic level, it's pretty easy to characterize friction. Like if you have wood on steel, it's almost always within a certain range of coefficients of friction, okay? So anytime you have 2 surfaces in contact, you get this thing. And here is the relationship between friction and the normal force that we sort of referred to. So what's going on here is this is kinetic friction. We're going to start with kinetic friction. Kinetic friction is equal to this thing called the coefficient of friction times the normal force, okay? What do you notice about the normal force and friction? What do they not have that they usually have? They're not vectors. And there's a reason for that, because if they were vectors, they'd have to point in the same direction. But we know, for most of the problems we've done, they're perpendicular to each other, right? If I'm sliding this thing, my phone, across the table, friction points that way, it's slowing it down, and the normal force points up. So pretty much always, friction and normal force are perpendicular to each other. And that's why we don't write this as a vector, right? This is a proportionality thing, which means that, and this should make some physical sense, right? If I'm sliding the phone, if I press down on the phone, is it harder or easier to slide? Harder. So as we increase the normal force, the frictional force is also going to increase, okay? And the coefficient of friction, so what are the units of friction force? Newtons. What are the frictions of the frictions? What are the units of normal force? Newtons. What do you think the units of the coefficient of friction are? Well, this would be Newton squared, right? So if you go from Newtons to Newtons, does this have units? No. It's what's called a proportionality thing. It's probably a better word for it that I am not remembering. But the coefficient of friction is really a function of the material properties of the 2 surfaces that are in contact. Okay, so wood on wood has a particular range of coefficient of frictions. Steel on wood, steel on steel, wax on, all these different things. So any 2 combinations of materials that can slide across each other have a range of coefficient of friction. The way we get them, we just run experiments. And so people make these big tables where they run a bunch of different tests of different materials. And that's a lot of engineering is just big tables, right? So that's all been characterized. And we'll actually do a lab today where we look at the coefficient of friction of a wood block sliding on another piece of wood. Okay, so we'll know the range, and then we'll be able to measure it using force diagrams and stuff like that. So that's how we define friction. Yeah. Okay. I covered all the things. Cool. We're going to try this example, which means I'm going to try to set this up. So, okay. We have a 10 kilogram crate, and we push it with a force of 50 newtons across a floor that has a coefficient of friction of 0.3. And we want to know what is the acceleration of the crate. So first off, we want to draw our crate, right? So here's our floor. Here's our crate. All right. What are the forces acting on this crate? Normal force? Normal force. Oh, come on. That's supposed to be red. Normal force. And you'll notice sometimes I write normal force capital N and sometimes lowercase n, and it doesn't matter. They're all the same. Okay. Gravity, which it will call mg now. That's weight. Okay. What else?
Push.
Pushing force. That's, let's say it's moving this way. We'll call that F push. And friction. And that's kinetic friction. Okay. So we can redraw our force diagram. I figure we'll do this just XY, right? And so if we want to draw this as a free body diagram, we draw it over here. So X, Y, and we redraw these. So we have normal force, F push, weight, mg, normal, F push, and kinetic friction. And we know that the box we can just represent as a dot. So we want to sum up all of these forces. But the other thing we want to remember is, so first, Newton's second law, which says the net force is equal to the mass times the acceleration, right? And we also want to remember that the kinetic friction is related to the normal force by this formula. And remember, those are not vectors, okay? So these are the equations we're using. What do you think is a reasonable acceleration for this problem? Like 1 meter per second squared, 10 meters per second squared, 100 meters per second squared? Probably not 100, right? So let's say between 1 to 10. Okay, so that's the range we're looking for. So let's sum up all of our forces in the x direction and all of our forces in the y direction. We're going to start with y because that's the simplest one, okay? So if we sum up all the forces in the y direction, that's going to be equal to the normal force minus mg. So the sum of all the forces is equal to mass times acceleration in the y direction. What's our acceleration in the y direction? 0, okay? Where is our acceleration? Yeah, in the direction of F push, probably. So, because it can't be in the direction of friction, because friction can't make something change direction, right? It only opposes motion. So we'll also do the x direction, and that's going to be F push minus kinetic friction is equal to ma. And I'm just going to write a, it's acceleration in the x direction, but I'm going to assume you know that, okay? If we want to sort that out, that means we can rewrite this. So we can say, all right, we know N, normal force, is equal to mg in this case. Okay? So we write this as F push minus mu k, that's the coefficient of kinetic friction, times N, but we know N in this case is mg. So we've rewritten friction in terms of normal force and the coefficient of friction times ma. Okay, what are we trying to solve for? Yeah, we're solving for acceleration. So we want to know what is the acceleration of the crate. So we solve for acceleration. Doing some algebra, we say F push minus mu k mg over m is equal to a. And I'm going to move that over so we have more space. All right. And then we just plug in our numbers. So that's going to be 50 newtons minus 0.3, which doesn't have any units because it's the coefficient of friction. Mass is going to be 10 kilograms. Our G is 9.8 meters per second squared. And we divide all of this by 10 kilograms. Plugging in all these numbers, we get an acceleration in the x direction of 2.1 meters per second squared. Oops, I made an S backwards. Is this in the range of stuff we said made sense?
Yes.
Yes, so we're doing good. Okay. So sorry, if you're following along on the slides, we skipped around a little bit, but I wanted to get to friction before we actually talked about the lab today. So I guess that was what I was thinking. Cool. Any questions about this? So static friction is a little bit trickier. in the case of static friction is equal to the force of the push. Now this is by definition, right? What do we know about static friction? What do we know about the motion in static friction? You are not moving. So that means in the direction that you're pushing, the static friction has to exactly cancel out the amount of push that you have, okay? And so what that means in practice is, get a stool because the chair rolls. So let's say I'm pushing, is it following me? Good. Let's say I'm pushing this chair or stool, okay? So if I push here, let's say I'm applying 3 newtons of force that way, okay? What's the static frictional force? 3 newtons of force. What if I push harder and I push with 5 newtons? What's the static frictional force? 5 newtons of force. Now I push even harder and it starts to move, okay? Let's say at the point where I push with 6 newtons, I overcome static friction. Okay, what kind of friction do we have now? Kinetic friction, okay? So there's a limit to static friction. Until you reach that limit, the forces just have to cancel. Okay, so whatever force you put in, that's what static friction is. So kinetic friction is always just mu times n, pretty simple. Static friction is a little bit more complicated. It goes up with the pushing force until you reach a limit. So the way you figure out what the limit is the maximum static friction force is a different mu s, right? So this coefficient of static friction times the normal force, okay? So the normal force still impacts it. Like if I push down, the amount of force I need in this direction goes up because I've changed the normal force on the stool. So that means I need to overcome static friction differently, right? Because you can see it also depends on the normal force. So I'll have to push more in the x direction to get the same effect, okay? So what this says is once the pushing force exceeds the maximum force of static friction, which you can calculate based on the coefficient of static friction, then the object will move and it goes back to kinetic friction, okay? So what we mean, this has an interesting consequence in that the coefficient of static friction always has to be bigger than the coefficient of kinetic friction. And there's a really good mathematical reason for that. So if I'm pushing with 3, then 4, then 5, and I get to 6 newtons, okay, it takes more energy and more force to get something moving than it does to keep it moving, which if you have to move something heavy across your floor, you may have experienced, right? You have to make a big push to get it going, but once something is sliding, it's easier to keep it going, okay? So it's harder to get something going than it is to keep it going, all right? So the way this looks if you have this terrible animation that I made is like this. And so it also means that the maximum static friction force is also bigger than any kinetic friction force, right? Remember, the kinetic friction force is constant. So if you graph kinetic friction force, it should be a flat line, right? You add more pushing force, it doesn't change the friction, right? So if I push this thing, once it's sliding, I can push it hard or I can push it not hard. The friction stays the same. It doesn't depend on how hard I push it. For static friction, it changes with how hard you push it, okay? So if you wanted to graph this, if you graph friction versus applied force, you can see it's linear, which is what we said, right? Static friction equals pushing force. So if that 1 newton, 1 newton, 2 newtons, 2 newtons, 3 newtons, 3 newtons, up until you reach the limit, which is the static friction max, which you can calculate. And then there's this part we ignore in this class because this is engineering right here, like this curve, right? And then kinetic friction becomes constant, okay? This is a very key point about friction. And the problems we're gonna have with this are like, you'll know the coefficients of friction, you'll know the pushing force, and a problem you might have to decide if you're dealing with static or kinetic friction before doing the problem. Okay, so that's why I'm going over this in such detail. Okay, that's just my aside, which I meant to put at the end of the class, but here we are. So let's talk about force and motion. So we're going to do a problem. I'm going to give you guys, so which gun would you like to do? We're not going to do all 3. What's your favorite gun?
Assault rifle.
Which one?
Assault rifle.
Okay, Great. Let's start with the assault rifle. So what we want to figure out the force of the gun on the bullet. So this is slightly different. So we've been doing projectile motion, but now we're not doing that. So what's happening is when you fire the gun, there's an explosion, and that creates an acceleration from here to here. Okay? Once it leaves the end of the gun, then it's a projectile motion problem. That's not the part we're doing. We're calculating the acceleration from here to here and using that to get force. Okay? So it's first a kinematics problem because we know the speed. So the muzzle velocity, what's that?
How fast it is at the end of the barrel.
Yeah, how fast it is leaving the barrel. So that would be the start of our projectile motion problem, but it's the final velocity for this problem. What's the initial velocity for this problem? 0. So the bullet starts here, you have an explosion, it accelerates from here to here and then becomes a projectile, okay? So initial velocity 0, final velocity 975 meters per second. The mass is in grams, so you'll have to convert that to kilograms. And the barrel length is really your distance in the x direction, okay? So you can use that to calculate acceleration, then use acceleration to calculate force. All right, I'll give you a couple minutes. Okay, so I'm gonna draw this. What color should we make our bullet? We'll make it pink. So assuming that just the basic function of a gun, you have a bullet that starts here. What's the speed, and oh, sorry, that's where the bullet starts, and then we'll call this the x-axis. So here's your initial position, here's your final position, okay? What's the speed at the initial position?
0.
Yeah, so v initial is equal to 0, and the final speed, v final is equal to 975 meters per second, okay? So we're given speed, let me just highlight that, and we're also given the barrel length. The barrel length would be our distance, okay? So we would call that, in this case, delta x. So we'll say delta x is going to be equal to 0.508, okay? When you fire the gun, that's going to create a force that we're going to assume is constant. It's not completely true, but it'll give us a pretty good estimate. And so that creates the bullet moving from here to here. So we want to start with a kinematics equation. So we know that we have, just to summarize, we have delta x is equal to 0.508. We have v initial in the x direction, which is 0 meters per second. This is in meters. We have v final, which is 975 meters per second. And we want to know acceleration. Why do we want to know acceleration? Right, force equals mass times acceleration, and we know we also have mass, okay? So eventually we want to figure out force is equal to mass times acceleration. We assume that the force, we don't even really have to draw a force diagram here. We assume the force is this way, right? We assume the acceleration is also this way. So we're going to first find acceleration. We're going to use that to find force. So in order to find acceleration, we're going to have to go back to the last few chapters and talk about kinematics. And we're assuming this is a constant acceleration because we don't have enough information to do anything else, okay? So the acceleration, there's an equation that doesn't have time, and it's this one. V final squared is equal to V initial squared plus 2a delta x, okay? I'm going to move this up here just so we have all of our equations that we're using together. We know that this is 0. So now we have v final squared is equal to 2a delta x. So we can solve for acceleration. That's going to be v final squared over 2 delta x. So we plug in our numbers. That's 975 meters per second squared over 2 times 0.508 meters. When you plug all that in, let me see, I hope I did this. Yes, that's going to give you 9.36 times 10 to the 5th meters per second squared. So remember, our last acceleration we found was 2, okay? That was for pushing a box. So much more acceleration coming from the gun, which hopefully is expected. I don't expect you to be able to estimate what the acceleration is here, but it's probably bigger than 2, okay? So that's our acceleration, and that's in which direction? X direction, which should be the same as force, okay? So then we go back to this equation and we say force equals mass times acceleration. Only problem here is we're given the mass in grams, okay? So this is a mass in grams. What would the mass be in kilograms? 0.006, I think. 0.06, yeah. Yeah, 0.06. So 0.062 kilograms, because there are 1,000 grams in a kilogram, so you just have to divide by 1,000. And then the acceleration we found, 9.36 times 10 to the 5th meters per second squared. And we plug those in, and that gives us something big. 58,000. 58,000 newtons, which is why you don't want to be hit by a bullet, because that's a lot of newtons. Just for reference, what's 1 newton? What's like if you have 1 newton, what's the weight of 1 newton? What's something that's similar in weight to 1 newton? It's probably not very big, right? It's like on the order of like less than half a pound. So an apple actually is a really good example, which is easy to remember because Newton is famous for possibly getting hit by an apple. That's probably just not true. But that's the story. You guys are familiar with that story, right? He's like gets hit in the head by an apple, and he's like, "Oh, gravity! Yeah." Don't think that happened. Mostly he was bored because I think there was like a plague, and so he did a lot of physics because he was trapped in his house. It was like quarantine for COVID, but I didn't do nearly as much stuff as that. I didn't invent any physics. I just had to homeschool my kids. It was much worse. Okay, so we have a force of 5,800 newtons. But the key to this problem is we're using all of the stuff we've learned so far. We used kinematics to figure out acceleration, and then we used the Newton's second law to figure out force. Okay? Any questions? Okay. Back to the other